Throughout the year, this year in AP Chemistry 1, you will need to utilize a variety of skills that fall in the category of math and chemistry. This video, in 2 parts, is intended to first take you through some examples and explain the basics of some of the mathematical things that you'll need to be able to do right away. And then part 2 video actually takes you through the worksheet that is attached to this math and chemistry note packet. What we would like you to do is complete the note packet as you watch the video, which will contain a variety of sample problems and then concludes with several worksheets. When you get to the conclusion of this video, you should complete the worksheets first and then watch the second video in order to check over your answers and make sure that you're on the right track. This video is going to cover the topics of significant figures, derived units, the metric system, dimensional analysis, and problem solving in general. So first, significant figures. Why are they important? Numbers in math versus numbers in chemistry. Up until this point, when you are solving problems in math, your teacher has probably told you, round your final answer off to a certain decimal place or a certain number of digits. The difference with numbers in chemistry is we are actually going to reflect the number of digits in our answer that reflect the accuracy of the actual device that was used to measure that particular value, or the accuracy level of the numbers that were utilized in the calculation to gain that value. The rules for significant figures are covered in the Let's Review section of your textbook, and they begin on page 35. And they cover rules such as zeros, zeros to the right, zeros in between, etc. So at this time, you want to hit pause on the video and go to page 35 in your textbook and read that page and the next page, which also includes some examples of the significant figures rules. When you've done that, you want to start the video up again, and as I solve each problem throughout this instructional video, I will apply significant figures according to those rules. First, before we begin solving problems, derived units. This is just a vocabulary reminder of what a derived unit is. A derived unit is a value that is calculated from other values not directly measured. Now, you have to be careful with volume because there are devices that measure volume directly, like measuring cups and graduated cylinders. But when I say volume as a derived unit, I'm referring to it as being calculated from a length, width, and height set of measurements. And so this unit is calculated from multiple values that are measured from a device, either the same device or more than one device. The metric system. The metric system can be taught in many, many ways. And what I'm going to show you here is the method that we feel is the most fundamental. If you have already learned the metric system to the extent that you are comfortable with the sets of conversion factors that you are using, that is not a problem. What is not acceptable is to use a sliding decimal method. You're going to need to be able to show your work via dimensional analysis. So if up until this point in school you've always struggled with the metric system, we highly recommend that you take this system on that I'm about to show you. And this system is predicated on the base always having a value of 1 and all the other metric prefixes being related to that idea of the base being 1. So for example, if we're talking about meters, this would mean that 1 meter would be equal to 1 times 10 to the negative 6th megameters. Now at first this can seem opposite of what you would think, but you have to remember that a megameter is a very large unit. So it would make sense that if you have a distance of only 1 meter, that the number of megameters that there would be in that 1 meter should be a very small number, hence the times 10 to the negative 6th. So you can create a conversion factor from any one of these on the list, and you do not have to relate them always back to the base. For example, I could look at kilometers and millimeters, again staying in meters as the base unit. This would mean that 0.001 kilometers is equal to 1,000 millimeters. So I don't have to include the base unit in my conversion factor. I can jump from one spot on the metric system to any other location on the metric system. And our base units are not only things like meters, but also we're talking about grams, liters, joules, and many others that we'll see throughout the year. As I move into the first problem-solving task with dimensional analysis, unit conversion, or factor label method, which are three terms which are synonymous, let me also stress the importance of, if you do not have the metric system conversion factors memorized at this point, they will need to be committed to memory for our first chapter test. For the summer assignment quiz, you are allowed to use your handwritten notes, not this note packet. So I would recommend that not only, as it says at the top, would you include table 1 from page 23, but it also would be wise to have the metric table that you see in front of you in those handwritten notes for use on the summer assignment quiz. So the summer assignment quiz will get at, do you know how to use these things? And by the time we get to our first unit test, it will be, have you committed those to memory? Okay, so now into dimensional analysis. What is it? It is a method, a problem-solving method that's used to convert one or more units to other units, and that can include both the metric system and other conversion factors. So, for example, how many seconds are there in a day? So this is designed to show you how to utilize the dimensional analysis method. And you really have two choices. What you see in front of you is oftentimes nicknamed the picket fence method, and this method is fine, but you have another choice, which would be the fraction method, and I'll just show you what that would look like. And it's just two different styles of how you write it. And so you'd write 1 day times 24 hours over 1 day times 60 minutes, again over 1 hour, times 60 seconds over 1 minute. And both of these are essentially the same thing. It's just two different styles, the picket fence method or writing it as actual fractions. Now, when it comes to entering this in your calculator, we just want to make sure we're clear about how that process would work, regardless of how you show the work on paper. When you're working across a dimensional analysis problem, any number that's in the numerator, like 24 for example, is multiplied, and you're going to do this all as one string of math, and any number that's in the denominator is going to be divided. Now, in this particular problem, all the denominator values are 1, and we all know anything divided by 1 is the same, but just for explanation's sake, I'm going to include the ones as I talk you through how you would enter this. So in your calculator, you would enter 1 times 24 divided by 1 times 60 divided by 1 times 60 divided by 1, and then enter. And you will get 86,400 seconds. Now, when it comes to the significant figures, how do you apply them in this particular problem? This is an example of where you would not, because all of the conversion factors and the original number, 1 day, because it's counted, are considered exact. So you would just carry all digits as provided by your calculator, 86,400 seconds. What I don't want you doing is multiplying the top, multiplying the bottom, writing down those intermediate values, and re-entering them to divide. Please do this all as one string in your calculator. It reduces the opportunity for errors. Next, let's see if we can do one from scratch. Express the quantity of 1 foot in different dimensions, both inches and meters. So we're going to do this as two separate calculations. So I'm going to start with 1 foot. And I'll use the picket fence method first, and I'll convert it to inches. And then, just so you know about your spacing, we'll repeat the process and do 1 foot and convert it to meters then below it, and we'll use the fraction method, just so you can see them both. So in the case of feet, yes, you are expected to know the basic conversion factors within the English or customary system. 1 foot is 12 inches. And this would be considered, I made my fraction line a little long there. This is considered an exact value. The 12 inches equals 1 foot. Now next we're going to go ahead and do this in your calculator. So 1 times 12, I hope we can do that in our head, comes out to 12. And then when we go to write our answer, we would just write 12. Well, not exactly. We need to apply significant figures now. So in this particular number, there were 3 significant figures to start, the 1 and the 0 and 0. Zeros that follow the decimal, meaning to the right, are considered significant. So I need 3 digits in my final answer, multiplication rule, 12.0, and then my final label. Now, one thing I neglected to mention on the previous example is the reason this method works is because whatever unit I have here then also appears here, which means those units cancel out. And my final answer would be 12.0 inches. Now below, 1 foot to meters. This is going to be a little bit more lengthy conversion. So first I'm going to go ahead and change it to inches, just like I did in the previous problem. And then I'm going to continue on by changing it from inches to centimeters and then centimeters to meters. In the next slide, we will actually record the common conversion factors between the metric and the English system. But for now, if you're not familiar with it, 1 inch is in fact equal to 2.54 centimeters. And then our third conversion factor, 1 meter, is 100 centimeters. And this comes from the metric table that we talked about previously. Canceling of units, feet, inches, and centimeters. Now all that remains is the 1 meter. 1 times 12 times 2.54 divided by the 100. Our answer comes out to 0.305. Now, why have I rounded it to 0.305? Because these are my 3 significant figures that correspond to 3 significant figures in the beginning of my problem, and then finally adding my units. So again, this particular conversion factor goes back to the metric system that we talked about at the beginning. This is a conversion between metric and English, and I will provide you with 2 more that will help you with the major systems, mass, weight, mass, length, and volume. And this is a conversion factor within the English or customary system. So what are those important conversion factors that you're going to need to know? And for the previous problem, again, this one comes from the metric system or the metric table from previously. This is one more conversion factor. This gets at mass. On the previous slide, we did the length, which was 1 inch equals 2.54 centimeters. And that will take you through what you will need for this packet. If you run into other conversion factors that you need when you're working through your problems, for now, you should look them up online. But we will talk about which conversion factors are necessary as we proceed throughout the school year. So next we have a series of example problems going from more simple to more challenging, starting with how many centimeters cubed are there in 2.570 liters? 2.57 liters. You're also going to need an additional conversion factor here to be successful that relates to centimeters cubed and how that relates to what I refer to as fluid volume or volume that's not in cubic units. And that's that 1 centimeter cubed is equal to 1 milliliter. And this is a conversion factor that it's going to be important for you to know throughout the year. So knowing that, along with our conversions from the metrics table, 2.57 liters, step 1 is I will want to change it from liters to milliliters. 1 liter, because it's the base, is 1,000 milliliters. Step 2, 1 milliliter equals 1 centimeter cubed from above. Do you need to show this conversion factor since it's 1 to 1? Yes, because otherwise you cannot show your true unit analysis. And this final answer will come out to 2,570 centimeters cubed. Significant figures. This value contains 3 significant figures, so does this. This 0 is a trailing 0 where no decimal point is present, which means, by definition, it is not a significant 0. How many inches are equal to 4 kilometers? 4.00 kilometers, and this time I'll use the picket fence method. First step is I want to change this from kilometers to centimeters. That's going to then allow me to use the conversion factor that we used before, which is that 1 inch equals 2.54 centimeters. So using my metric table, 0.001 kilometers is equal to 100 centimeters, followed by 2.54 centimeters is equal to 1 inch. These conversion factors, although the metric to English conversion factors, meaning 1 inch and 2.54 centimeters, are rounded off and not considered exact, we can consider them exact for our purposes in class and use our original value of 4.00 to determine our significant figures. Metric conversions are, by definition, exact. So we'll have 3 significant figures in our final answer, which will be 157,000 inches. Combined units. Combined units are an example of which are units in both the numerator and the denominator. So here we have 80 kilometers per hour. This is an example of one that's really going to show why I like the picket fence method for emphasis when you're dealing with something. I'm just trying to straighten that up a little bit. When you're dealing with combined units, because it prevents you from making the mistake of putting a fraction in the numerator. The units that are in the numerator go on the top of the picket fence, and the units that are in the denominator go on the bottom of the picket fence. And now I'm ready to make my conversion, and it wants my final answer in inches per minute, which means inches over minutes. So it doesn't matter if you convert the time unit first or the distance unit first. I always like to start with a unit in the numerator just for organizational purposes. So I'm focusing now on getting from kilometers to inches. So once again, I'm going to use the same conversion factor that I used previously. 0.001 kilometers is 100 centimeters, and then 2.54 centimeters is 1 inch. So this is a conversion we've done a couple of times now. And now the unit analysis, kilometers will cancel and centimeters will cancel, and I have inches in the numerator as what I want in my final answer. Next, I'm going to work on the hours to minutes. The hours are in the denominator, so they'll appear in the numerator of my next step. It doesn't matter that it's skipped over several steps. And I know that 1 hour is equivalent to or equal to 60 minutes. And so that will complete my time conversion. Hours and hours cancel. And now math straight across. 80 times 100 divided by 0.001 divided by 2.54 divided by 60. And your final answer to this one should be 52,000 inches per minute. Now, why 52? Why 2 digits, 5 and 2? Because there are 2 significant figures in the 80. This particular trailing zero is considered to be significant because of the decimal point being placed next to it. Next, 150 kilometers squared to millimeters squared. So in this one, again, I'll switch up my method and use fractions just to show you that it doesn't matter which you choose. It's a style thing. And the conversion factor that we have here, even though it's squared, which means it's in 2 dimensions, we're going to treat it like it's a normal linear 1-dimension conversion. So that means 0.001 kilometers is 1,000 millimeters. Now this conversion factor will only convert 1 dimension. How do we make it squared? We simply square the conversion factor. So the only difference is how you handle this in your calculator and the addition of the parentheses in 2. So in the calculator, this is going to be 150 times 1,000 caret 2 divided by 0.001 caret 2. So that's squaring both the numerator and the denominator. You can use parentheses in your calculator and then put parentheses around the term and square it only once. I just prefer to square each value in the term. Both will give you the same answer. We want 4 significant figures in our answer, and it's going to make sense to put this number into scientific notation because of its size. 1.500 times 10 to the 14th, times 10 to the 14th millimeters squared. Now, how do you know when you should put a number in scientific notation or not? Honestly, when the power of 10 starts to get up around 5 or larger, that is where you're reaching the point where it makes sense to go ahead and put numbers into scientific notation. If it's been a while since you've worked with scientific notation and you think that you've forgotten how to handle that, that is also covered in the Let's Review section of the textbook, which you'll be looking at next, starting on page 32. Finally, in this section, volume conversions. This is where the volume conversion in this is actually the denominator unit. Overall, this is a density value, but the volume conversion is in the denominator. So now we have 3.50 grams per kilometer cubed. So this is a combination of both the volume unit in the denominator, and it's a combined conversion because it's got both numerator and denominator. So step one, I'm going to handle the grams to kilograms first. Grams is a base, 1 gram, 0.001 kilograms, again from the metric table, and now handling the cubic unit. So in the squared example previously, we simply squared the conversion factor. In this example, when it's cubed, we simply cube the conversion factor. 0.001 kilometers for every 1 meter. I put parentheses around that term, and I'm going to cube it. So when I enter this in my calculator, it's going to be 3.50 times 0.001 times 0.001 caret 3, and then the divided by 1 caret 3 won't affect the answer because 1 cubed is 1. Our final answer comes out to 3.50 times 10 to the negative 12th kilograms per meter cubed. 3 significant figures in the original number, 3 significant figures in the final answer. Next, we have a series of sample problems that are a little bit more challenging in these 3 boxes. I'm going to take you through each one and show you how to do the calculation. If you would like and you're starting to feel confident with these, you can pause the video at this time and try doing sample problems 1, 2, and 3 independently, and then watch along with the video. Or if you still feel you need a little bit of reinforcement, you can solve the problems along with me as I walk you through them. Okay, in sample problem number 1, a piece of copper has a mass of 57.54 grams. It is 9.36 centimeters long, 7.23 centimeters wide, and 0.95 millimeters thick. Calculate the density in grams per centimeter cubed. Your first step in this problem is going to be to organize your information. If you look at this, we know we can calculate the volume from volume equals length times width times height. So in this particular case, here is our length, width, and thickness is another way of stating height. All of these are in centimeters except for the height is in millimeters. So that's going to cause a problem when we go to do this calculation. So you have a couple of choices. I'm going to show you how to do the conversion directly in the formula. So the length, 9.36, the width, 7.23, and now the height. It's currently 0.95 millimeters, and we need that to be in centimeters. So converting right within the problem, 1,000 millimeters equals 100 centimeters. So I know when I enter this into the calculator, I'm going to do 9.36 times 7.23 times parentheses 0.95 times 100 divided by 1,000 close parentheses. The next natural question is, can I cancel this and get rid of the 100 and take this down to 10? And the answer is that yes, you can, but you'll get the same answer either way. So when we calculate this, we would get a final answer of a volume. But then I'm going to make the suggestion that rather than doing this just as a volume problem, you could also do this portion that you see here, right in the density part of the question. So if I were going to do that, I would have density equals mass divided by volume, and in the denominator of my fraction, I would put everything that you see listed there for volume. The other choice is to calculate that answer, carry extra digits, and then place it in the denominator here. Or I'm taking this whole quantity and bringing it down here to the denominator. Either way, when I'm finished and I round it off to the appropriate number of significant figures, my density will be 9.0 grams per centimeter cubed. Now, why 9.0? Why 2 digits in my final answer? Because of the 0.95 millimeters. In 0.95, there are only 2 significant figures, the 9 and the 5. Sample problem number 2. Mercury has a density of 13.6 grams per centimeter cubed. What is the mass of 95 milliliters of mercury in grams? How about in pounds? Now, it also gives you a little note there underneath. It says, first note that 1 centimeter cubed equals 1 milliliter. We will use this exact conversion factor throughout the year, so you need to memorize it. And we used it previously as well in this lesson. So this wants us to determine the mass in grams and pounds. So this is a density problem, but instead of solving for density, we're going to be solving for mass. So we have to remember that density equals mass divided by volume, and then we're given some information to start with. We're told the density is 13.6 grams per centimeter cubed, and we're also told that the volume is 95 milliliters. Now, the first question wants to know the mass of mercury in grams. That one's going to be pretty straightforward because I currently have density in grams per centimeter cubed, and I currently have the volume in milliliters. And since I know 1 milliliter equals 1 centimeter cubed, then I can either simply arbitrarily change this centimeters cubed to milliliters, or I could have arbitrarily changed this milliliters here to centimeters cubed. Either one would be appropriate. I am going to erase this and go with changing the 13.6 grams per centimeter cubed to grams per milliliter. And again, it's because those are interchangeable. So now I'm ready to go ahead and plug into my formula. So I have 13.6 for density equals mass divided by 95 milliliters for the volume. And so now, just a little algebra, cross multiply. So I'll end up with M equals 13.6 times 95, which is 1,300 grams. 1 and 3, 2 significant figures because there's only 2 significant figures in 95. So that is one of my answers, the mass in grams. The next thing it asks for is the mass in pounds. So the easiest thing is to take my answer in grams and simply convert it to pounds. But the answer in grams was not exactly 1,300. 1,300 is my rounded off answer. So when I'm going to take an answer from a previous step and use it to calculate something else, I shouldn't use the rounded off answer. I should carry additional significant figures. So the number in my calculator was actually 1,292, etc. So I've carried 2 extra significant figures. And now the conversion factor between pounds and grams, as I gave it to you earlier in this lesson, 454 grams is 1 pound. My grams will cancel, and my final answer, rounded now back again to 2 significant figures, 2.8 pounds. And the final sample problem in this section is sample problem number 3. Stoga garnet paint has a density of 0.914 grams per centimeter cubed. You need to paint a wall in the front hall that is 7.6 meters long, 2.74 meters high, with a paint layer of 0.13 millimeters thick. What volume of paint in liters is required, and what is the mass in grams of the paint layer? So in this particular one, very similar to sample problem 1, we're going to use V equals LWH. But the actual volume is an answer in this particular practice problem, so we have to do the V equals LWH as a separate step, at least here initially. And also, it eventually wants our answer, it wants to know what the mass will be in grams that we'll need. And our volume here and our density is in centimeters cubed. So it's going to make sense to just want to go ahead and have all of our dimensions in centimeters as well. So that way when we do LWH, we'll end up with centimeters cubed and not require an additional conversion. So when I put them in here, I'm going to convert them as I go. So the first one is 7.6 meters long. So 7.6 meters, and my conversion is going to be 1 meter is 100 centimeters. Now my width, this listed as height, but again, it's going to be 3 dimensions. It has length, height, and thickness, but those again are our 3 dimensions, so we'll go with that one next. 2.74 meters, same conversion, 100 centimeters is 1 meter. And last but not least, we have 0.13 millimeters for the thickness of the paint, and this is going to be a different conversion. Milli is 1,000, and centi is 100. So now I can do this complete conversion and solve for volume all as one big step in the calculator. 7.6 times 100 times 2.74 times 100 times 0.13 times 100 divided by 1,000. And my final volume is going to be 2,707.12 centimeters cubed. Now I'm not going to box that because that's not my final answer because I haven't rounded it off to the appropriate number of significant figures. I did write it down that way though to show you that that's what the numbers should look like when you see what you have on your calculator. It asks, what's the volume of paint in liters? So I'm still going to need to convert that further for the volume final answer. So now I'm going to use the picket fence method, and I'm going to convert this from centimeters cubed to liters. 1 centimeter cubed equals 1 milliliter, the conversion factor you have to commit to memory, and 1,000 milliliters is 1 liter according to the metric table. So essentially here we're dividing by 1,000. Now I am going to round it off to 2 significant figures as I write down the answer. Why 2? Again, it goes back to the 0.13 has only 2 digits. So this will round off to 2.7 liters of paint. So one of my answers is that I'm going to need 2.7 liters of paint. The second question said, what's the mass in grams of the paint? I originally, when I calculated the volume, first calculated it in centimeters cubed, so I would have the correct unit for the density portion of this problem. So now I'll switch colors to just show I'm moving on to the next part of the problem. D equals m over v. It gave us the density in the original question as 0.914 grams per centimeter cubed. We want the mass in grams, so we're in the correct unit, and we have the volume in centimeters cubed. And notice once again, I'm going to go back and use my full digits, not my rounded off answer, because this is not going to be a final, because we're using it to get a different answer. So we don't take the 2.7, we take the raw number, for lack of a better way to describe it. This is going to be cross multiply again, so m times 1 is going to be m, and 0.914 times 2,707.12, and this will come out to, now round off to 2 significant figures as you look at your number from your screen and transfer it to your paper. Why 2 significant figures? Even though the 0.914 has 3 in it, one of the values that contributed to the volume, again, was the 0.13, and it only had 2 sig figs, so my final answer can only have 2 sig figs, or significant figures. Sig figs being the short way of saying that. So 2,500 grams. These zeros are not considered significant because the decimal point is not written. If I want to show that zeros, trailing zeros like this, are significant, I have to place the decimal point. This concludes the first half of the math and chemistry lesson. So at this point you're going to stop, complete the worksheets that are attached to this packet, and then watch the second video, which will take you through the solutions to those. This particular packet, the math and chemistry packet, you may not use on the summer assignment quiz. You may only use your handwritten notes. So anything you learned from this process that you want to include in your handwritten notes, you must add. And again, it has to be handwritten. It cannot be computer generated in any way, shape, or form. Good luck on the worksheets.